Welcome to section 4.2, Theory of Polynomial Functions. So, a theorem we have is called the Intermediate Value Theorem, or IVT. If we're given a polynomial p of x with real coefficients, if for real numbers a and b, the values of p of a and p of b, so the y values, have opposite signs, then there exists at least one real zero between a and b. Well, what does this mean? For example, if we're looking at two x values, let's see, one of them is, again, as we mentioned here, a and b, and our outputs are up here and here. We know if one of them is a positive and one of them is a negative, then it must cross the x-axis at some point, right? And since it crosses the x-axis at some point, we must have some zeros somewhere in between those positive and negative signs for my y values. All right, example 1. Show that the polynomial function p of x equals 3x cubed plus 7x squared minus 5 has a real zero between -1 and 1. All right, so the way we're going to be able to show that it has a real zero, or at least it exists at least one, is we're going to show when we plug in -1 and 1, their p values are going to have opposite signs. So let's see. So p of -1 is going to equal -1 cubed plus 7 times -1 squared minus 5. And then we can calculate it out and we get -1. So if I was to graph this value, we have at the x value of -1, our y value is -1. And then let's check the next one, the +1 value. So, okay, we'll go ahead and plug in +1. That'll be 3 times +1 cubed plus 7 times +1 squared minus 5. And when we calculate that out, that will give me 5. So at the point +1, and somewhere up here at 5, we have another point. And again, remember, our polynomial functions are continuous. There's no gaps in them. So we know at some point, however my polynomial function looks, wherever it crosses here, at some point, in order to get to the next point, it has to cross the axis at some point. We don't know where exactly, at least at this moment, but we know it has to cross at some point. And when it crosses, that would be an x-intercept, or a real zero. So again, because the signs went from being a negative to a positive, we know somewhere along the line it needs to have crossed the x-axis. So then we know that there's at least one real zero between -1 and 1. All right, dividing polynomials by a binomial x minus k. So divide 3x cubed plus 7x squared minus 5 by x plus 1. So we'll go ahead and do this the long division way. 3x cubed plus 7x squared. Now we're missing the x term, so I'm going to go ahead and just pop in the x term as a placeholder. We haven't changed the value, it's just a placeholder, because I did 0x. And then let's go ahead and do some long division. So I'm trying to figure out what number I'd need to multiply x by to get 3x cubed. And that number, let's see, x, that would be 3x squared. So 3x squared times x would give me that 3x cubed. That's my main goal. But then I have to remember, when I'm multiplying, that's going to be 3x squared times the x plus 1, which would be 3x cubed plus 3x squared. And I'll subtract this amount from my polynomial. So 3x cubed plus 3x squared. And again, my hopeful term, hopefully, I'm going to cancel out that first term right there. And indeed, it does cancel. And then I have 7 minus 3. So 7 minus 3 is going to be 4. And then we'll bring down that 0x term. Okay, so we finished one cycle. So my next cycle, now I'm trying to figure out x times what would give me 4x squared. So x times what would give me 4x squared? Well, that would be 4x. So go ahead, add 4x up here, and then I'm doing 4x times that x plus 1, again the x plus 1 right here, which would be 4x squared plus 4x, and that is what I'm going to subtract from my polynomial. And those two cancel out, and let's see, I am left with 0 minus 4x, so that's going to be negative 4x, and then bring down the negative 5. All right, so what are we doing so far? We have one more cycle to go, or at least hopefully. So the question is, how many times can x go into negative 4x? Or x times what gives me negative 4x? And that would be negative 4. So now we're going to do negative 4 times the x plus 1, which is going to equal negative 4x minus 4. And this is what we're going to subtract from our polynomial. And let's see, so negative 4x minus 4. So these two will cancel out. And again, that is our goal, for them to cancel. And then we're left with negative 5 minus negative 4. Negative 5 minus negative 4 is going to be left with negative 1. So I have a remainder of negative 1. How would I write that as my answer? Well, our final answer is just going to be the 3x squared plus 4x minus 4 plus my remainder, which is negative 1, still being divided by the x plus 1 from over here. And that's how we'd write it out. Again, the part that perfectly divided, and then the remainder. All right, so division of p of x by x minus k. If p of x has degree n, then the quotient polynomial has of degree n minus 1. So again, when we're dividing, the degree should go down. The remainder r is a constant, maybe 0, and the complete quotient for p of x divided by x minus k is our quotient plus the remainder over our divisor, which I did up here. So again, the quotient plus the remainder divided by the divisor. Now, so up here we had to use all of the variables and had a lot of signs that are going around, which can be a little confusing sometimes. So we're going to look at something called synthetic division, which is dividing without writing out all the variables. The one thing about synthetic division is we use it for linear divisors. Okay, like x minus 1. We would not be using x squared minus 1, not a linear divisor. Okay, so use synthetic division to divide 3x cubed plus 7x squared minus 5 by x plus 1. So we're going to do the same thing we did from example 2, but this time we'll use synthetic division, which means we're not going to be working with the variables. And it's a little different when we do synthetic division. If we're dividing by x plus 1, we want to find the number we're going to divide by. So we'll set the divisor to 0 and solve for x. So we're going to be dividing by negative 1. So I'll set up my synthetic division like this. Again, negative 1 coming from our divisor when we set it to 0. And then we'll go ahead and put in our polynomial, but again without the variables. So a positive 3, a 7, and then again that x term is not there, so we'll do a placeholder of 0, and then negative 5. Now, to start the process, we'll go ahead and drop 3 down, and we'll multiply negative 1 times the 3. And negative 1 times 3 is going to be negative 3. Now, this is where it's different. We're going to go ahead and add. So 7 plus negative 3 is going to be 4. And then, again, we're going to go ahead and multiply the negative 1 to the 4, which is going to be negative 4. And then again, we'll go ahead and add, which is going to be a negative 4. And one more time, again, let's go ahead and multiply negative 1 times the negative 4, which is going to be positive 4. And then negative 5 plus 4 is going to be negative 1. Now, how do we figure out how many variables we're going to have? But again, remember, based on our, I went a little too far. There we go. The quotient polynomial is going to have a degree of n minus 1. Okay, so we can use that to figure out what the degree of our synthetic division polynomial is going to end up with. We originally started with an x cubed, which now means we're going to start with an x squared. So this would be a 3x squared plus 4x minus 4. Just go down in power. And then again, this last one here is going to be our remainder. The value here, if it ends up being a 0, we know that that number divides perfectly into our polynomial. If there's a number at that last part, that's going to be our remainder. So plus our remainder of -1 divided by, again, our divisor of x plus 1. Which you'll notice is the same thing we had above. So there's a great way of using synthetic division. A little different method, but it's nice because it's shorter. But again, you can only use linear factors to divide into. So example 4, use synthetic division to divide x cubed minus 3x squared minus x plus 3 by x minus 3. So again, to figure out what we're dividing by, set it to 0, so x is going to be 3. So we're dividing by 3. And then set in our polynomial, so that's going to be a positive 1 from the x cubed, -3, -1, and 3. We don't have to add a 0 anywhere because we're not skipping degrees. It goes perfectly from cubed, squared, 1, and then no variable. All right, so starting the process, we'll drop the 1, and then it'll be 3 times 1, which is going to be a positive 3. And then again we add, so that was going to be a 0. Again, following the method, 3 times 0 is going to be 0. Again, adding, that'll be a -1, and then 3 times -1 is going to be -3. And then 3 times -3 is going to be 0. Aha! Again, remember, the last number we get, if it's a 0, we know that this is a perfect factor, or it would be factoring our quadratic, or not the quadratic, factoring our polynomial. And that 3 is a 0 of our polynomial, if this ends up being 0. Because again, we have a remainder of 0, which means it perfectly goes into our polynomial. So again, we'd say remainder is 0. So 3 is a 0 of the polynomial. Because when I put 3 into our polynomial, it'd make it equal to 0. Now, let's take a look at the remainder theorem. If p of x is divided by x minus k, the remainder is equal to p of k. So the opposite of whatever is in that binomial, if we input that number into our polynomial, whatever the remainder is going to be equal to if we had inputted that value into our polynomial. So moving on to the factor theorem. A polynomial p of x has a factor x minus k if and only if p of k equals 0. So again, remember above, we found out that the value of 3 would give 0, which would mean it would be a factor, or x minus 3 is a factor of our polynomial. So let's go ahead and work with that concept. So example 5, for the polynomial, a 0 is given. Find all other zeros. So we're given the polynomial p of x equals -x cubed plus 4x squared plus 7x minus 28, and we're given the factor of, or we're given the 0 of 4. So we already know 4 is a 0. How do I find the factoring of this? Well, usually it's best to use the synthetic division. So I'll go ahead, set this up for synthetic division. And let's go ahead and start dividing. So multiplying, that'll give me the -4. Adding, that'll be 0. 4 times 0 is going to be 0. 7 plus 0 is 7. 4 times 7 is going to be 28. Adding that together gives me, 0. So now I do know it is indeed a 0. Because again, my remainder is 0, which means it is indeed a 0. How does that help me? Well, remember, I now know how to make the other polynomial from the remaining numbers. We just take it down 1 power, so it's going to be an x squared instead of an x cubed. That'll be -x squared plus 0x plus 7, which I can simplify down to negative x squared plus 7. That's what's left when I divide it by the 0 of 4. And remember that 4 is a 0, which means we know that x equals 4, or that x minus 4 equals 0. So this is my other factor. It's x minus 4. Now, are we done? Well, that is about as much as we can factor. So since we're done factoring, we know this is what our polynomial is factored. To find the remaining zeros, I'll take again my new binomial and set it to 0 to find my other zeros. Okay, again setting it to 0 to find the other zeros. We'll add the x squared to both sides. And now to solve, let's go ahead and take the square root of both sides. Again, remember, when you do the square root property, you have to include the plus and minus, that there are two possible answers. And then we get plus or minus the square root of 7 equals x. So those are my other two zeros. So my total zeros are 4, positive root 7, and negative root 7. So again, how did we find this? Well, first we did the long division, or not the long division, the synthetic division. We found the new polynomial when it's divided, and then we set that to 0 to solve for the other zeros. Now example 6, use the given 0 to factor the polynomial into linear factors. So the plan is to use the synthetic division to divide the polynomial up into smaller and smaller polynomials and eventually just be able to factor it. So let's go ahead and start the division. Setting it up. We don't skip any exponents, so we don't need to add any zeros. We'll go ahead, drop down the negative 6, and start out the process. So negative 5 times negative 6. And then, let's see, so negative 17 plus 30, going to be 13. Again, negative 5 times 13, negative 65. Add that up, we get a negative 2. Negative 5 times 10 is going to be a positive, or negative 5 times negative 2 is positive 10. Aha! And we end up with 0 as the remainder. So we know negative 5 is indeed a factor of it, which means we can now rewrite our polynomial as x plus 5, which again comes from our k value. Remember, x equals negative 5, which means x plus 5 must equal 0. So we have x plus 5. And then, so we're using a cube, which means we factored it into the next exponent down, which is going to be x squared. So I have negative 6x squared plus 13x minus 2. Alright, so we're close to being done, but again, we want to factor it into linear factors, and currently we have one linear factor and then one quadratic factor. So we have to figure out how to factor that. Can that be factored, that trinomial? Well, I'm going to go ahead and pull out that negative. So take the negative out, pull it out front in front of them all, which will be 6x squared minus 13x plus 2. Can we factor that? We can. That trinomial 6x squared minus 13x plus 2 can factor into 6x minus 1 times x minus 2. Again, if you need any help or review on factoring trinomials, please let me know. Okay, so now we went ahead and we factored it into linear factors. Again, linear meaning we have an exponent of 1 on all of the variables, and we're done. So the synthetic division helps us break our polynomial down into a lower degree polynomial, and then we can continue factoring it. Alrighty, so question, what if we are not dividing by binomial x minus k? Well, then we're going to have to just go ahead and do the long division. Alright, small typo right here. So let's go ahead and do the division. We're dividing by x squared plus 1, but notice we've skipped the x value, so we'll go ahead and add that placeholder of 0x, and then plus 1. And then again, doing regular long division, we have 3x to the 4th. We're missing the x cubed power, so I'm going to go ahead and add that in as well as a placeholder, plus 0x cubed, which again doesn't actually change the value. plus x minus 6. All right, so we're looking to figure out x squared times what would give me 3x to the 4th. So that would be 3 times x squared. Okay, and then multiplying that out to the whole trinomial right there, we will get, let's see, that'll be 3x to the 4th, plus again, that's going to be 0x. And then plus x squared, or 3x squared. That cancels out there. That also cancels out, and then we have the negative 2 minus the positive 3, which will give me negative 5x squared. We'll go ahead, drop these terms down. And again, now we're on the next cycle. So finish the first cycle, on to the next one. Now let's see, what do we multiply x squared by to get a negative 5x squared? So what do we multiply it by to get a negative 5x squared? Well, we need a negative 5, and that's it. That's all we'll need. So negative 5. And then now we'll go ahead, start multiplying that negative 5 out to, again, that whole trinomial. So that would give me the negative 5x squared. That times that would be 0. And then negative 5 times the positive 1 is going to be negative 5. Okay, doing the subtraction, cancels out. Positive x minus that is just still going to be a positive x. And then negative 6 minus negative 5 is actually going to be a negative 1. Now, let's see. Can my x squared go into this value? It can't. So we're done. That's going to be my remainder. We can't divide in anymore. So my answer can be written as 3x squared minus 5 plus, and again, the remainder divided by the divisor, which is x squared plus 1. And then we're done. So again, with the linear terms, if you're dividing by a linear term, you can use a synthetic division. If not, go ahead and do it by long division. Alrighty, that is it. If you need any other resources, like practicing factoring trinomials or anything, please send me an email. If not, have a great day.